Myself, Dr. S. Priyadarshini, heading Department of Mathematics, JJ College of Arts and Science, Autonomous. This video is about the course Abstract Algebra for 3rd BSc Mathematics students, and the particular topic is from Unit 1 Permutation Group. So now, definition for permutation group. A permutation of a set A is a function from A to A. It has to satisfy the condition, that is the function 1 to 1 and on to. In array notation, consider a set A equal to set of all elements 1, 2, 3, 4. Here we are having two permutation in the set alpha and beta. That is, alpha is mapped with the elements 1 to 2, 2 to 3, 3 to 1 and 4 to 4. And beta is from 1 to 2, 2 to 1, 3 to 4 and 4 to 3. So I have explained here, that is alpha of 2 is mapped with the element 3 and alpha of 4 is identity, that is again mapped with the element 4. Similarly, beta of 4, element 4 is mapped with the 3 and beta of 1 is mapped with the element 2. Also we have identified again an element beta of alpha of 2, that is we have to go from back, that is beta of alpha of 2 means element which is mapped with 2 in the permutation alpha. So alpha of 2, what is that? Alpha of 2 is 3. So now again we have to move from backward, that is 3 element mapped in beta set is what? So beta of 3 is mapped with 4. That is the final answer. Okay. Here again we having a composition for permutation with beta to alpha. So just keep it in your mind. We have to move from alpha to beta, back to front. Keep it in mind. Okay. So reverse is alpha, front is beta. Okay. So we have to identify the mapping for 1, 2, 3, 4 from back side. So what is the mapping from 1 back side? 1 is mapped with 2. Moving to front, 2 is mapped with 1. So the resultant is 1. Similarly, next element is 2. We have to move backward, that is 2. 2 is mapped with 3 and in front position 3 is mapped to 4. So the final answer is 4. 2 is mapped to 4. Next one is 3. Go back. 3 is mapped to 1 to front. 1 is mapped to 2. So the final answer is 2. So 3 is mapped to 2. Next 4. Go back. 4 is an identical mapping. 4 is mapping to 4. Move front 4 to 3 and 3 we have to get the final result. 4 is mapped to 3. Similarly, we can identify for any permutation this composition function. So again I am revising the permutation definition. A permutation group of a set A is a set of permutation of A that forms a group under function composition, right? Now we are going to see about the example. So the set of all permutation on the set 1, 2, 3. So 1, 2, 3 is a symmetric group which consists of 3 elements 1, 2, 3. Okay. So there are 6 permutation. So we can state as 6 permutation from the formula n factorial. If the number of elements is n factorial is the number of permutation. Here the number of elements is 3. Therefore the number of permutation is 3 factorial. What do you mean by 3 factorial? 3 into 2 into 1, that is 6 into 1. So 6 permutations that I have stated, 1, 2, 3, 3 permutation, 3 factorial, 3 into 2 into 1 equal to 6. Okay, now we're going to see some properties of this symmetric permutation 3. No. What are all the elements that 6 permutation bring? Number 1 is identity, number 2 is alpha, 1, 2, 2, 2, 3, 2, 2, 3 to 1. And next one is alpha square, that is alpha, composition with alpha, you get 3, 1, 2. Next beta 1, 2, 3, 2, 1, 3, 2. Next alpha beta 1, 2, 3, 2, 2, 1, 3. And next one is alpha square beta 1, 2, 3, 2, 3, 2, 1. So whenever you carry this composition function with any more elements in the under 6 category, you will get the resultant in the 6 results only. You can't get rather than above this result. Okay, if you make a composition function with alpha to alpha square beta, whenever it is alpha square to beta or alpha square to alpha beta or alpha to alpha beta, you will be get the same resultant again within this 6 permutation. I think you are all clear, right? So now we're going to check whether the symmetric group 3 is a group or not. So what is the condition of a group? So we know that a group is a set. It has to satisfy 4 condition under its operation, right? So the 4 conditions is closure, identity, inverse, and associative. But in particularly, we have to clear about that associative, identity, and inverse. If it satisfies the 3 condition, okay, then we can say that the particular set is a group and in particular operation, right? We know here the operation is composition. Now we have to verify whether the permutation set is a group. Okay, so first thing is associative. Okay, composition of a function is always associative, which is a standard result, right? We no need to check about it. Next, identity. What is identity? 1 is mapped to 1, 2 into mapped to 3 into 3. Okay, we are also having in permutation, so identity is clear. Next, inverse. Since permutation are 1 to 1 and on to, there exist inverses also permutation. Therefore, it is cut and clear that the S3 is a group. Similarly, we have to find this result for Sn also. So here, just we are checking that whether any more permutation exists rather than 6. So we are calculating alpha cube. Whenever we are trying to calculate alpha cube, we get the result identity 1 to 2, 2 to 3, 3 to 1, 1 to 3, 2 to 1, 3 to 2. So we have to start from reverse. 1 is mapped with 3. Here 3 is mapped to 1. So 1 to 1 identity mapping. Back side 2 to 1 to front 1 to 2. Again identity 2 to 2. From back side 3 to 2, 2 to 3. Again the resultant is identity. Next, beta square 1 to 2, 2 to 3, 3 to 2. Move from back 1 to 1, 1 to 1, identity 1 to 1 result. Next, 2 to 3, 3 to 2 identity, and 3 to 2, 2 to 3 again identity. Okay, so whenever you have to start from new result, you will yield the back already existing result. Okay, so here we have some example for this computation. You can able to work out from the previous result, and you can identify, you can receive only the 6 permutation again and again. Okay, now the general formula for Sn. So we have to consider a set of all elements with n elements, 1 comma 2 comma etc. n element, and it is denoted by Sn with n permutation, and the number of permutation is n factorial, right? Similarly, the same procedure. Now dihedral 4. How to find the dihedral permutation? R0 is an identity. R90 you have to rotate slightly starting from 2, 2, 3, 4, 1. Next, R180 is you have to start from 3, 4, 1, 2. Now R270 is start from 4, 4, 1, 2, 3. Now horizontal position 2, 1, 4, 3. Now vertical position 4, 3, 2, 1. Next, diagonal position, that is 1, 4, 3, 2. Next, diagonal, cross diagonal, that is 3, 2, 1, 4. These are in the diagonal for 4. Okay. Next, main results. Every group turns out to be a permutation group on some set. And cycle notation, shortcut of cycle notation. If 1 to 2, 2 to 3, 3 to 1, you can write this as 1, 2, 3. That is 1 is mapped to 2, 2 is mapped to 3, and 3 to 1. Identical should not be represented. Similarly, for beta, you can see 1 is mapped to 2, 2 to 1. So just short out the first cycle 1 to 2. If you close the bracket, that is a cycle. Next, 3 to 4, 4 to 3. Therefore, 3, 4. It indicates another cycle. Now, disjoint cycle. 2 permutations are disjoint if the sets of elements moved by the permutations are disjoint. And also, every permutation can be represented by as a product of disjoint cycle, as I stated the before example. Also, permutation is denoted by pi, and A be the identity permutation represented by an empty list of cycles, and While there exists n with permutation of n, it should not be equal to identity of n. So these are the examples for the short composition of cycle notation. You can see here. Thank you.